Okay, let's resume. Here. Okay, so we've seen the very basics of formulation of an reinforcement learning problem, in particular an NDP. Let's see an intuition of how this apparently trial and error process may actually work. So here what we say is valid in the context of an NDP. But that's the core of any other algorithm, even in a deep learning setting, okay? And this, at least in my opinion, the very basics necessary to understand a bit more technically how this trial and error process may effectively work. So, usually in reinforcement learning, the policy to be learned is denoted by pi. And again, this policy is meant to maximize the expected discounted return. Let's try to analyze all the three terms. So, first, the return, usually denoted by u, is the sum of rewards obtained over time. So when you speak about return, at some point t in time, that's all the rewards accumulated that the agent got in his lifetime. That's called the return. The expected return, as we said, is because given a probabilistic MDP, where state transitions can be probabilistic, you are not always sure about, given this state, what is the reward I can get in the future. I don't know. It depends from this probability distribution, so you must take the expectation. Basically, it's just a weighted average if you want. You average the rewards in all the branches for the probability of picking that branch. The discounted term is basically just you can see this is a mathematical trick to simply keep infinite horizon problems manageable. Okay, so you discount the return. It means that if your decision problem is non-terminating, usually when we have reinforcement learning in mind, we have in mind to train an agent, and when we achieve a given, I don't know, quality of training, okay, quality of behavior, measured whatever, we don't care at the moment, we deploy the agent, and that's it. Then the agent goes by itself, does what it needs to do. And so usually this behavior should be infinite. So the discounted term is simply to discount rewards, so decrease, okay, decrease the magnitude of rewards, so that sooner or later, and this depends on the discount factor, from a given t onwards, from a given point in time onwards, the rewards will be zero effective. So you can turn any infinite horizon problem into a finite horizon problem. That's just more or less a mathematical trick. This discount factor, that is actually the gamma parameter here, okay, that is the factor that realizes this idea of discounting the rewards, is obviously a factor that must be comprised from between 0 and 1. And there's another interpretation in truth that is especially used in robotics. So you can read about it in these two different ways. The other acceptation is that the discount factor tells you the probability that the robot will fail at some point in the future. Okay, so at some point in the future the robot will stop working. So the end of battery, I don't know, obsolescence of the actuator and sensor, whatever. And that's another way to say basically that your infinite problem is in truth finite, because sooner or later the robot will be, I don't know, to charge the batteries, to do something else. An intuition. So what is this formula? This should be quite easy. I'm not a mathematician. I'm a computer scientist. Okay, so maybe I didn't mention this. I graduated in computer engineering, science and engineering, and a PhD in computer science and engineering. I'm not a mathematician, but even I can understand that here what we are calculating is the expected return at a given point in time according to the current behavioral policy. So the mapping between state and actions that the agent is using. Could be a random policy, okay? At the very beginning of training, this is a random policy if we don't have any bias or heuristic. And how is this calculated? You need to sum over this potentially infinite horizon all the rewards that you will get discounted by this part. Okay, that's it. That's simply what the expected discounted return is. And again, we have an expectation simply because the reward can be a non-deterministic function, so we can sample multiple rewards depending on the state that we take. Some intuition about the discount factor. The discount factor is a bit critical because many times there is the question about, can I set the discount factor as I wish? Or is the discount factor something that is given to me as part of the problem definition that I need to take? Okay, this is not really clear in the literature, at least in my opinion. So my answer would be, if you have a problem that involves a potentially infinite decision problem, okay, but in which your agent can actually fail or can stop working for some reason, such as a robot that needs to charge the batteries, whatever, okay, try to set the discount factor accordingly. So, I don't know, my robot needs to charge every t time steps. Try to configure a discount factor such that more or less around those t time steps, the reward goes to 0. So you are optimizing for the right problem. Instead, if you have a problem that you can define and design, basically you have more freedom. You can choose your own discount factor, and this choice basically follows this implication. If you look at the formula, putting gamma close to 0, or 0 obviously, at one extreme, basically means that immediate rewards worth more than future rewards. Okay? Because every time you sum all these rewards, you have an additional multiplication by this gamma discount factor. That is at most 1, so you can only reduce the reward. You can never increase the reward. If you have a reward of 10, you can have at most 10 or less. So, basically, putting gamma close to 0 means my agent should mostly care about immediate rewards. It should strive to give more importance to immediate rewards. Obviously, if you keep gamma close to 1, you have the opposite. Basically, because if you have 1, it means that you are in an infinite horizon. Every reward matters in the future. Okay? So, usually, reinforcement learning problems properly set up, not properly set up, sorry, but problems that are actually worth dealing with reinforcement learning, being sequential decision-making problems with rewards that are delayed in time, usually have a higher gamma. Usually. But it may happen, okay, to also have, I don't know, higher failure probability. It means having a lower gamma, basically. My robot is I want to model a problem in which my robot is very unstable, and I can't foresee too much in the future. I need to take decisions that have, for which I value more immediate rewards. Let's do this. So this is just the definition of the expected return that we said, expected discounted return, that we said is the quantity that the reinforcement learning agent wants to maximize always in a single agent set. How to do so? Here, the very first, let's say, technique that has been proposed in the 80s, I would say, if I remember correctly. There is a very famous book by Sutton and Bartow, that took these equations and developed them. So, how can I actually, we said that the goal is basically to learn a behavioral policy, so a mapping from states to actions. And the reason that the agent performs actions is to achieve a state which is the goal, basically, of the goal state in the environment. So basically, the agent should try to do what? The agent should try to understand what are the most desirable states to be. That's what he must do. Let's do an example of a maze, then we will see some example. In a maze, I could say that more or less, there are caveats such as the walls and whatever, but more or less, the closer I am to the goal, the better I am. Okay, so being in a state close to the goal might be more worth than being in a state far from the goal, far away from the goal. Okay, so to do so to try to estimate the worthiness of being in a given state, this Bellman, scientist, introduced the so-called Bellman equations after himself. They have been called afterwards. And the first one that we see is the so-called state value function, denoted by V pi in a given state. So, the state value function is exactly what I described. The worthiness, the value of being in a given state with respect, obviously, to the final goal, okay, of my role, of my agent. And we can express this state value function as it is written here. So it is the expected return. The vertical bar is the conditioning operator. So you have a probability distribution and do condition on being on this state. So I only focus on the events in this probability distribution for which I am in a specific state. So the value of being in a given state S is the expected reward that the agent can hope to collect from that specific state onwards. That's the value. Okay. Given our definition of expected return, expected discounted return, we can expand and basically say that the value of being in state S is the immediate reward that I got in the state in which I am, plus, obviously, the discounted return from that state onwards. So we are just expanding the definition of the expected return, right, in one step. Current reward and the future ones. So we just extracted the current reward from this expectation from t to infinity. Now we want to compute these solutions, so we need to use computers. Computers are not mathematicians. They don't really like the expectation. Because expectation is not really something you can actually handle with a computer. So let's try to work with this expectation. What does it mean to have an expectation? As we said, the transition functions can be probability. So the expectation can be expanded in this way. The value of being in a given state is, let me check, okay, is the reward I got in that state by doing that given action that transitioned me to another state. This is the immediate reward, okay? The reward that I took in time step t according to my action. Then I have a recursive definition, okay? My reward the reward that I got now, this is the reward function. So RSAS prime is the evaluation of that function for those parameters that give me an R, lowercase r. And then we have a recursive function basically. So this reward plus the discounted value of the next state that I will obviously calculate in the same way. And what is this about? This is the expectation. Let's try to analyze this because it seems complicated, but it's not. Since the transition function, the state transition function can be probabilistic, I need to take to consider all the possible future states that are reachable from this current state given this current action. Okay? Because this T, if you remember, is a mapping to a probability distribution between 0 and 1. So I need to consider that given this state and this action, there may be more than one outgoing arrow from my given state to the next one. And also, obviously, I need to consider that my policy, given a state, also my policy can be probabilistic. So, given a specific state, I may have multiple actions to carry out, multiple choices. So, we start to expand, let's say, the expectation and make it computationally tractable. We sum over all possible transition probabilities from that state to the next state, multiplied by the probability of doing that specific action according to my policy. Let's try to be more clear. To compute the expectation, okay, expected return from this state onwards, I need to take every action, support or charge, okay, multiply the probability of that specific transition. I can go in this state. If I do support, I can go into this next state, or I can go into this next state. So the same state repeated. So I need to take the probability of doing an action. In this case, I would say that the action is deterministic, but it could be probabilistic, and the probability of going to one or the other state. And that's how you expand the expectation. So this is just the, let's say, computationally tractable, okay, specification of this mathematical form. And what does it give me? As we said, the worthiness of being in that state. This is a number, okay, a scalar, like the reward. If I have two states and one is a higher number, it means that on average, to be more precise, in expectation, the state with the higher V number has a better chance to give me a higher reward. So that's the best next state to try to pick. So I need to do an action that brings me to that specific state with a higher probability. Okay? Let's try to clarify even more. This is just an example of, let's say, a fictional NDP. So we basically have a sort of a maze, if you want. So we have a starting position of the agent that is the bottom left corner, if I remember correctly. And we have a goal destination, which is the green tile. And instead, I don't know, a wrong destination, a hole, I don't know what it is, I don't remember. But again, a place to avoid, a tile to avoid, which gives -1 as reward. Here, the gray box is an obstacle, okay? And our agent obviously needs to learn to achieve the goal destination. That is the green tile. We have, let me check, where is the interactive, okay? This is the one I wanted to show. So I don't know why, but here you have +1, here you have -1. I don't know why it is a bit scrambled. This is our starting position, okay, I was right. So this is a MDP. So to achieve the goal, we don't care if we are here, we don't care if we got here by following this path, or if we got here by following this path. It has nothing to do with me reaching the goal. Okay, so that's an MDP. We have a sparse reward scheme if you want, because the only tiles from which the agent gets a reward are the 2 final tiles. So either the agent is dead, because I don't know, a robot fell off a cliff, or the agent got to the goal. So sparse reward. Sparse reward means that until the agent navigates here, it has no clue about whether it is doing a good job or a bad job. So intuitively, a sparse reward scheme is usually much more difficult than a dense reward scheme, because you have no clue what you are doing until you get to a catastrophic situation or the goal situation. So usually, even if you have a problem whose most natural reward scheme is sparse, so I need to do that, the only reward is when you do that, usually your first task when engineering the problem, the learning pipeline, is let's try to translate the sparse reward into a dense reward. Let's try to devise out additional reward signals. That's usually what you want to do, because a sparse reward is very different. So our agent starts. We don't know, we haven't spoken yet about a specific reinforcement learning algorithm. The only thing we know is that this agent will do actions according to a policy. Which policy? Well, if the agent knows nothing about the environment, let's say that the agent only knows whether it is in the winning or in the losing tile, there is basically no heuristic you can use. You just do at random actions until you get to the goal. So if we will do random actions, meaning that the agent could do go here, go down, go here, go down, go right, go left, go right, go right, go left, go left, go right, okay? Okay, that's how reinforcement learning works in a nutshell. Until it reaches to a point with a reward. Only then the agent can say, okay, I got +1, so by applying our formula, I got a reward. I can now compute the value of all the states I traversed while reaching that tile. I can now, because I have the immediate reward. I can take the first state and I can see which action I took, in which state I got, and then all of this is multiplied for the actual reward that I got. Obviously, if I get a reward of 1, that reward will be diluted in all the states that I visited. It simply stems from the formula, no? You have a multiplication here. One multiplication here, one multiplication here. Okay? So, this is, if we click play, we see these values, and now I would say the values are stationary. They no longer change. And if you can see, let's start, and if we click here, we go one by one. We can see that at every step, what is a step here? Basically is a computation of that Bellman equation that we have seen, so of the state value function. We can fill a tile. So when we see that this number appeared here, we can imagine, okay, the agent got to the goal, and now doing the computation recursively, that's a recursive formula, we can try to distribute this reward across all the paths that the agent followed. let's see what is the path that the agent followed. See? Probably he went up, down, right, left, okay, because he can fill multiple slots. See how the values spread? How can the values spread? Here is my reward, the only reward that I sampled, okay? So here we are in a situation in which the agent only got to the goal, never went to the wrong position. So now I can say, given the formula, I can say, since I got this reward, and the probability from this state of going there, or of going there, or of going there, so I apply the formula, I can say, okay, the value of being in this state is pretty high. It makes sense. I'm close to the goal. Now that I have this Vs, the value function of this state, I can compute the value function of the neighboring states, because that is a next state for all of the neighboring ones. And in fact, you expand both. Sorry. You can expand both. The value of being in this state is 0.78. So, given the discount factor, given the transition probability of the environment, given my probabilistic policy, if any, I can calculate with that formula that the value of being here is slightly higher than the value of being here. Can you guess why? Why are they not equal? Because the distance to the goal is the same. The agent cannot move diagonally. So if I'm here, I need to do 2 correct actions to get to the goal. But even if I'm here, I need to do 2 correct actions to get to the goal. So why one state value is higher than the other?
Maybe because it's closer to the worst.
Exactly. This one, it is true that it has the same distance to the goal. But in this state, I can also get to the wrong state. So it is much better to be here. Obviously, given that the agent cannot move diagonally. If the agent could move diagonally, we can argue that probably this would be a higher value, because here you have 2 steps, here you have only 1 step. Okay, we could argue. But if the agent cannot, being here is for sure better than being here. This makes sense even if you count all the whole Manhattan distance. Here is a grid word, so the Manhattan distance is always the same. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it makes sense. Okay? And these calculations stem from the value function that we define. And if we go further, we can propagate better the values, and also the old values change, okay? Why? Simply because the agent accumulates experiences and can better distribute the final reward across all the visited states. So again, here this state dominates this state, also this state dominates this state, even if they are the same Manhattan distance. Also this state dominates this state. And we can see that even in this state, I can assign a value function. Okay, there's nothing wrong. Whatever state I have a state value function value for, I can propagate that value to the possible previous states. Okay. And again, with experience, the agent will refine the values up to a steady state. So, for instance, here, I think that now they don't move. No, they still move. They still move. Probably now they don't move. Yes. I would say that now iteration 13, we don't know exactly what this iteration is. Is it the times that the robot has achieved a terminal state? Is it the number of iterations in the recursive definition of the function that we did? We don't care. Okay? We only care about, we have a formula, okay, that given the reward and given the transition of the state transition of the environments, can estimate the value, the worthiness of being in a given state. So from this value, it is evident that this path is better than this path. Exactly because we have a -1. Otherwise, most probably, without this red tile, most probably the two paths will have the same values. Probably not really, because here you have additional tiles, so you can waste time, but they could have more, for sure, more similar values. So this is how you can use the function K. And as we said, one important thing to keep in mind that we will mention afterwards is to compute the state, the value, sorry, a scalar of a given state, of any given state. In that example, we computed the value function for any given state. You must know the reward function and the state transition function. They are in the formula. And this should immediately raise an alarm in your head, because we said that in reinforcement learning, usually we assume that we don't know the reward function and the state transition function. In fact, these equations were proposed in a framework that is called dynamic programming. The name is a bit unfortunate because it has nothing to do with dynamicity. But I don't know, at the time, the author thought it was a good idea to call it dynamic programming. And it is not reinforcement learning. There is nothing to learn here. This is simply similar to planning. Okay? I know the state transition function. It means that I know that from here, from any tile, I know which tiles I can get to. In a proper reinforcement learning formulation, the agent would have no clue what are the reachable states from a given state, unless the agent actually visits that state. Okay? Here instead, all of this calculation can be done without moving the agent at all. Because I know the state transition. It's like a robot that stays still, and since it knows the state transition dynamics, so what if I move forward, and it knows the reward function, so where are the rewards, the agent can stay still, imagine the paths, and compute the best path. Like you, when you need to drive somewhere, and you mentally decide which road to follow. You know the state transition function. You know, okay, here there is a road, then I can turn left, then I can turn right, and there is the destination. You can do that because you know the state transition function. And the reward, obviously, which is where is the goal. If you remove those two, for now, we should say that the formula doesn't make sense anymore. We will see that there are ways in which you can still use the formula. But again, even if this is not a reinforcement learning solution, a reinforcement learning algorithm, this gives you the idea of what most reinforcement learning algorithms try to do. Without knowing these two, they still try to recover this estimation. Most of the algorithms that exist try to do this. Besides the state value function, we have another value function that is very similar, that is the state action value function. So if you think about it, the state value function gives you the worthiness of being in a given state. And to do so, to calculate such value, you need to take into account that in any given state there are multiple actions you can possibly do. So a state action value function is more fine-grained. This tells you the worthiness, not of being in a given state, but of doing a given action in a given state. So it is actually a more fine-grained way to select the action. Basically, this is just a trivial extension to the previous value function. Why I say a trivial extension? Usually we call this function not with v, but with q. Okay, so q, the value of doing a given action in a given state according to a given policy is called q value. Before we have the v value. And now what is the trivial extension? Here we have the recursive definition as before, with q instead of v, as before. Now, compared to the previous situation, we have to explicitly take into account the action. Okay, so here we need to take into account which specific action that I need to select. Now we add two summations for the expectation, the actual action and the state transition given that action. Here instead, let's see, the summation over the action is inside. Because now I want to know the value of being in a given state and choosing a specific action. So I don't need to sum over the actions here for the expectation. That's the difference between the two forms. The rest are the same. Now that we have these two value functions that are very similar, you can even say they are more or less interchangeable. I mean, if I know that being in that state is better than being in another state, and I also know which action is more likely to bring me in that state, I'm fine. It's the same as knowing, given this state, my best action is this. It's the same. I just did a step more. So now it is quite easy to define what is an optimal policy. An optimal policy is a policy that always picks the best action or always picks the best next state. That's it. It's a trivial definition of optimality. Yes?
So a policy is not the optimal behavior in general, but is the current optimal behavior. And an optimal policy is the
yeah, so you can distinguish between an optimal policy that usually we denote probably in the next slide with pi star, okay? And that is the policy that guarantees you to get to the higher, to the optimal expected return. Then you have your policy without objectives, just a policy, which is the mapping between states and actions, so that you use to select actions. So for instance, as I said before, when you start with training an agent, okay, with reinforcement learning, your first policy is random. Because all of the state value functions or state action value functions that I can calculate are zero. I don't have any information.
So the policy needs to be updated.
Exactly. So now, up to now, we didn't actually define what a policy is.
Yeah, because I thought, given the second slide, it was the optimal behavior, so the policy was already optimal.
No.
So now,
yeah.
Optimal policy, it was confusing to me.
No. The goal is to get to the optimal policy, and usually you start with any policy. If you have some heuristic, some bias that can be used, you can use it as your starting policy, but then you should update the policy towards the optimal one. If you have no heuristic whatsoever, no information about how a likely policy, an optimal policy would likely look, you start with a random policy. And now, up to now, we never define the policy. We only define the expected return and these two measures, so the state value function and state action value function. So now, your question anticipates what will come next. now we will need a way to improve our policy. Our starting policy, random one, whatever you want, to improve that policy to make it become the optimal one. So here we have the optimal Q-value is the maximum Q-value that I can achieve in this state. So this number, this is a number as V, guides my action selection strategy. If I am in a given state and I have 3 actions, one action has a Q-value of 8, one action has a Q-value of 10, and one action has a Q-value of 20, I will choose the action with a Q-value of 20. That's the best action as far as I know. And the same for the state. The optimal state to be is, given that my next states are 2 states, one with value 5 and one with value 10, I will try to go into the state with value 10. Okay, so this, the Q-value, the state action value function, is more fine-grained because it directly tells you what is the best action. Instead, the value function only tells you what is the best state. You need to devise out what is the best action then. Okay? Why there is this distinction? A legitimate question will be, why not only using Q-values? I mean, they directly tell you, it depends. Some algorithms bypass the Q-values and try to estimate this value function for some reason that we are not really interested in right now. So, basically, your optimal policy in any given NDP is the policy that always picks the best action or the action that leads you to the best next state. And in fact, by rewriting the equations, okay, this is just a mathematical issue. In the equations, both the Q-value and the V-value, we explicitly referenced the policy, right? But as your colleague was saying, what policy? I mean, the policy up to now, yes? So you can rewrite those equations without an explicit reference to the policy. And then it's very easy to show that the optimal policy to follow in a given state, remember that the policy is a mapping from state to action, so given a state, what is the best action? Is no longer max, but arg max. So not pick the maximum Q-value, the Q-value is not an action. So this couldn't be a policy, it would be ill-defined. Pick the action that leads to the optimal Q-value. That's the argmax operator, okay? So pick, given all the Q-values that you have available in this state, one Q-value for each action. In our example, here, in each tile, I have 4 actions. Left, right, north, top, bottom, okay? So, what we are saying is that, given that we define the optimal Q and V values, trivially, also the optimal policy is trivial. Just always pick the best action. That is, the action that leads to the maximal Q value. That's the optimal policy. Right? Or not? Makes sense? So, remember that we have a very important assumption, okay? That we are able to estimate these values in the first place with 100% accuracy, because we know which state leads to which other state and what reward I can get for any given state. So we assume to have a lot of information, to know everything about the problem. So here, the main takeaway is that if I want to implement this strategy to find an optimal policy, and I use find and not learn on purpose, you're not learning anything, you don't need to create a simulation of your environment, to launch your robot in the environment and whatever. You just need to do math. That's it. That's a closed form solution, okay? You can compute it. You can compute it maybe. If the state space is too big, if the transition function is too big, if the action space is too big, the problem could be computationally intractable. But mathematically, this is completely feasible. Okay? So the optimal policy is called a greedy policy because it amounts to simply choosing the best action. And you cannot make mistakes. Okay? If you estimate all the state action combinations or all the states, you do not make any mistake. You immediately can calculate your optimal policy. I don't know how to say better, but you can put this system of equations in MATLAB and find a solution. That's it. You don't need to simulate anything. Your agent doesn't need to learn anything. No. All the estimations are correct at the end. And this is actually dynamic programming. A family of algorithms to compute, not learn, the optimal value functions and policies. Value functions include the state value functions and the state action value functions, so V and Q. As we anticipated, the main drawback is we assume complete knowledge of our MDP. So in particular, we know T and R. This dynamic programming family of approach two kind of further families. Policy iteration means I never look at the value at V. What did I touch? I don't know. I never look at the V value, okay? I only look at the Q values. So first I need to, policy evaluation means evaluate how good are the states to which my policy will lead, and then refine the policy. Instead, value iteration combines both steps into one. These are just some terminology that you may encounter if you read papers on this subject. And again, this can be an algorithm that is not a learning algorithm, but this is a general actually algorithm for policy iteration. So let's try to get at least an intuition of what it does. Initialize a policy. If we don't have any bias, any heuristic, any information available, initialize the policy randomly. Initialize all the V values for all the states, 0. I don't know anything yet. And then you repeat what? A policy evaluation step and a policy improvement step. These two macro parts. Until policy stable means what we did in our grid work, until the number don't change anymore. Okay. What we do in policy evaluation? For each state in S, we apply the formula, the equation that we mentioned before. So for each state, we know every state, we know every state transition function, we just apply the formula. Until the value of each state doesn't move anymore. If you remember when we hit play or when we went step by step, the values change until they reach a steady state. When you did this, so at the end of this first loop, what do you have? You have the 100% accuracy value estimation of every state in your problem domain. Now you can improve the policy. So you have a random policy, you are still with a random policy, and what you do for each state, according to your policy, you memorize the action that you did, and then you update the policy with the best action according to the value function that you computed before. Why you memorize the old action? Because you need to do this loop until you no longer change the best actions. It means that you learned the best actions in any situation. So the policy converts. Here, the state value converges. Here, the policy converges. If the old action is different from the new action, then the policy is not stable. You need to redo only this loop. This you can do once and for all. If the old action is equal to the new action, your policy is stable. And that's it. You found, and you didn't learn, you compute the best policy. We can see an example actually on the same domain that we analyzed before. In the previous example, we focused on the value function, state value functions. So we had numbers. Okay. We had numbers in the tiles, in all the tiles, because the numbers were the v-value of each state. Okay. Now we replace the numbers with an arrow, and the arrow symbolizes the best action. Since the action is go north, go south, go east, go west, we can put in any tile, in every tile, the best action. Obviously, here we are at the beginning of the process, and again, we are not yet learning anything, we are just computing the best policy. We initialized our policy, that is simply a mapping, not at random actually, but go left, go always left. I mean, what is the difference with random? If we have no clue, whatever initialization you choose is a fair initialization. Now, if we do the same as before, so we click step by step, we can see that the arrows begin to move. For some reason, always go up. Apparently, if we evaluate the state value function for every state, then it converges until it converges, so until every tile has a fixed number, like in the previous example. When we start evaluating the policy, the first modification that we do to our policy is, it is always best to go up. I mean, it may be. It depends on which action I choose in a given state and whether that action led to a better value. Let's try to be intelligent. Does it make sense that the first modification we do is go up? Absolutely yes, because we already know from before that the best path is this. So the first step that I must take, that I agent must take, if I'm starting here, is up. That's why the first modification is go up. Then left, then up, then right. Now it starts. Let's see. You can see that not every time everything changes. Here we don't know exactly what's going on behind the scenes, but behind the scenes we are evaluating every single state and what is the best action in that specific state. So again, maybe we start with only the starting state and the best action is go up. Then go up and go right. Then for some reason here we go back. And they don't move anymore. See? So we have go up, sorry, I did all the steps. Go up. This didn't move, this didn't move, this moved, this moved. See? Then why go back? Well, the only hint that we have, the only clue that we have to guess why go back is actually due to this. Okay, the algorithm may prefer to be on the safe side. Okay, so always go in this path. Remember that here there is nothing that measures how long did it take the agent to get to the exit. right? There is nothing. The only reward is +1, -1. So, for us, it doesn't make sense to go here and then go back. You are wasting time. According to the reward function, this makes perfect sense. Because if you remember, in the previous case, we had that this path always had higher values than this other path. So basically, with this reward function, we are saying to the agent, we don't care about how long does it take, but be safe. Basically, we are saying this. So the reward function shapes the policy of the agent. And now the values are steady, they don't change anymore. Okay? This is reset when you get to the end. So again, if we had, for instance, a dense reward scheme with these two rewards, but also let's say -0.1 in every tile. Why -0.1 in every tile? I want you to be fast. Basically, I am saying the agent, I want you to be fast. Don't lose time. Go straight to the reward. In that case, it could have been that this arrow would go right, because I'm wasting time. Maybe 0.1 is too little, maybe 0.3 would be something more meaningful. This value iteration basically is a compact form in which you only evaluate the states, and then basically you have this argmax policy that always picks the best action that gives you the best future state. But this is just a way to imagine the algorithm implemented for value iteration and policy iteration. There is no actual difference. You converge to the actual optimal solution every time, in this case. So again, for the last time, this is computing the optimal solution. If the problem at hand is computationally tractable, and you can afford the computation time, you have a powerful machine, or the problem is very simple, if you know T and R, stick with that solution, because that gives you an exact solution. It's always right. 100% you find the optimal policy, always. If you can't, either because the problem modeled in that way is computationally intractable, so you can specify all the state transition, you know all the state transition. You can specify the shape of the reward function, but simply the state space and the action space is too huge. I don't know, your computer, trivially, your computer runs out of memory, okay? Then you can turn to reinforcement learning. The other case is obviously, I don't know the state transition function. The problem is too complex, all of these states are linked in ways that I don't really fully know, so I can't specify T. Okay, then you can go with reinforcement learning. The first family of algorithms that we quickly see is a family of algorithms that is called temporal difference learning. Here actually we learn optimal policies, which means that the agent now can't do everything in imagination. So the agent actually needs to visit states to collect rewards and understand what's going on. In the previous cases, the agent didn't need to move in the grid and collect rewards. It could imagine what moving in the grid would cause. Okay? Usually in reinforcement learning you learn online, which means you update your policy while you are using it. It is not a separate stage in which you collect the data and then you run a training algorithm and you end up with a model. But you need to interact online with the environment. There exists nowadays also a variant of reinforcement learning which is called offline reinforcement learning, which is slightly different. But we don't cover it because it is not, let's say, the core idea behind reinforcement. And here is where the trial and error process that we mentioned in the very beginning with the first slide kicks in. If I cannot do these estimations, so if I don't know the state transition function, it means that I don't know what will happen to the environment if I chose action go up. Obviously in this example it makes no sense. If you go up, you go up. It is not so trivial. For instance, if you are here in the top row, if you go up, you don't go up, there is a wall. So the state transition function actually tells you here, if you go up, you end up in the same state. Now, we don't know the transition function, so the agent doesn't know what happens when it goes up. He needs to learn that. If the agent is in the starting position and goes up, it changes state. If the agent is already in the top row and goes up, nothing changes. He doesn't know. He needs to learn this. So he needs to bump into the wall. He needs to bump into the obstacle. He needs to fall off the cliff. He needs to get to the goal. Until the agent doesn't get to the goal, he doesn't know that there is a prize there. Up to now, instead, it knew where the prize was. It's there. I know R, capital R. Okay, now this is no longer the case. That's why the trial and error is needed. I need to explore the environment, to explore the actions and states. What if I go up? Okay, nothing bad happened, nothing good happened. Let's go up again. Okay, nothing good happened, nothing bad happened. Let's go up again, nothing changed, I bumped into a wall. Okay, maybe I should do something else in that state. Let's try to go left. No, bumping in the wall again. Let's go down. So if you can follow in imagination, we went up, then up again, nothing changed, then left, then we go down. In all of these moves, we have yet no clue about whether we are doing something good or not. There is no reward yet. We didn't collect any reward. So we need to do this trial and error process unless we get to some reward, positive or negative, doesn't matter. At least we have some feedback about what we were doing. So, what is the core issue in trying to devise a proper reinforcement learning algorithm? The issue that we already mentioned. We need to find a substitute for the transition function and the reward function. We don't know them. So we need to find something else to put in those formulas, basically. And in fact, the core concept of temporal difference learning, but in general, I would say of reinforcement learning, is replace the state transition function with an estimate of the value function. So we need to estimate. Now it is a proper estimate. Before, we spoke about estimates because it was an expected return, blah, 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 but we didn't do any estimate, actually. We did calculations, exact calculations. Now we need to estimate. Now we don't have the transition function, so everything that was here, we don't know what to put there. We need to find something else to put there. Both in the value function, in the state value function, and in the state action function. This term, so the one that substitutes the state transition function, is usually called an update target. So it is, I don't know how to say, it is a proxy. Something that I believe can guide me towards the correct behavior. We will obviously see examples of this update target, what we can put there. Basically, if you try to devise out what to put here, you are inventing a reinforcement learning algorithm, basically. because the rest of the machinery is the same, okay? How to update the policy, how to update the state action and the state value function is those formulas. What you need to do is, what can I put here? So you need to find a way to, okay, I don't have the state transition, but what do I have? I have samples of the state transition. If I do an action and end up in a given state, I have a sample. I don't have the complete environment state transition, but I have a sample. I know that if starting from state S and doing action A, I got to state S prime, I have a sample of the state transition function. Better than nothing, you mean. Okay, so basically what you do here is try to sample the environment, the state transition function and the reward function by acting in the environment online. So now the blue dot will move in the grid, okay? Up to now the blue dot stayed there because it didn't need to actually modify the environment. If we have, I don't remember, but I don't think so, if we would run the same visualization with a temporal difference learning algorithm, we won't be able to populate any numbers, any rows, until the blue dot moves. Right? Because we need to experience new states, new actions, new rewards. So this is, so to say, the general formulation of every algorithm of the temporal difference family, where, if you look closely, a new parameter appears, which is alpha. Alpha is an hyperparameter of your algorithm, basically. So every reinforcement learning algorithm, deep reinforcement learning algorithm, pick what you want, has a learning rate parameter, which was absent before, and now I will explain why. The learning rate is, it is not so easy to explain. The learning rate is the extent to which you learn from your experiences. Let's try to put it this way. How much do I change my current policy, so let's say my current Q values, depending on my current experience, so the reward I got in this time step. Do I change them a lot? I don't know, I modify one Q value from 1 to 10, or do I change them slightly, from 1 to 1.5? This basically means, as I said, how much do you give importance, relevance to your experience, to each individual experience. So every new state, every new reward and stuff like that. So alpha is another, like the discount factor, is another parameter that changes between 0 and 1. If you pick a higher alpha, learning rate, it means that you want to learn a lot from every single experience. I want to change my Q values as much as I can. What is the reasoning behind doing so? Well, if I change the Q values a lot, hopefully I will learn faster, no? Because I start differentiating all the different actions. So having a higher alpha means I try to learn as much as possible for every single experience. An experience means basically a triplet: old state, new state, quadruple if you want. Old state action, new state reward. That's it. If I set alpha slow, it means in a sense that I'm more cautious. I mean, that's just one sample. I cannot trust one sample too much. So let's be cautious, okay? Let's change my Q values a bit. That's what it means. So, a more, let's say, intuitive way of explaining this, but this is not 100% correct, is low alpha, slow learning. So it takes time, more time for your agent to learn. Computational time, wall clock time. Higher alpha, your agent learns faster. The caveat is, it doesn't mean that it learns the optimal policy. It learns something. Learning means changing the policy, okay? But we have no guarantee whether we are learning the optimal policy, a local optimum, something completely random. So, usually, when setting alpha, because it is an hyperparameter, so you need to choose it when you run your training in your agent, there is only basically one strategy. Pick the lowest alpha that you can afford. What does it mean? I have this machine. I want to do a given number of experiments. I have 1 month. Each experiment can take up to 2 nights. That's my alpha. I need to tune alpha the lower that I can without taking too much time. That's basically the strategy. There is no engineering methodology. Yes?
But if I have a limited time period of which I can run tests and I use a low alpha, I will get one policy and one hopefully optimum. But if that policy is just a local optimum, isn't it better to do fast learning and multiple fast learning?
Multiple fast learning, you means multiple experiments of the same kind.
Yeah, with different initial points. So maybe I discover 2 optimal policies that are both local, but not wasting time on one policy with the one.
Okay, so if I understand correctly, the question is, instead of running with a low alpha, one only experiment, can it make sense to run multiple experiments with different initial policies with higher alpha? Yes, it makes sense. The problem is, do you have any way to specify reasonably different initial policies? So do you have an heuristic, some bias? Because if you start with random policies, you don't know. But if you have some way to say, okay, these 2, 3, 4 initial policies are more or less good. Let's try to improve on them. Yes, it makes perfect sense to make to do what you mentioned. In general, if you have no clues, you start with random policy, blah blah blah. Yeah, the idea is try to keep alpha as low as possible, compatible with your the computational budget you can afford. Because again, learning fast means quicker convergence, but also high instability. It means, what does it mean? Stability, instability. If every time you sample a reward, an actual value, you change your q-values a lot, from one step to the other, your policy may drastically change. Drastically change means you can oscillate around the optimal. You can imagine, it is not different from any other optimization problem, okay? This is your solution landscape. How many times somebody put a random graph? No? This is your solution landscape. If you learn fast, let's assume you want to find the minimum. So this is the optimal star. This is whatever led you there, it's the optimal policy, pi star. I don't know. I start from here with my random initialization, or here, whatever. Every time I draw I do something, I get some feedback, hopefully, some reward sample, and I adjust my q-values. Having a higher alpha means doing this. Big jumps. Then from here, another big jump. Then from here, another big jump. Okay? Having a lower alpha, small jumps. Okay? So you are more steadily progressing towards, hopefully, the optimal. Just to anticipate a bit, if I end up here, how can I escape and end up in the true optimal policy?
I alpha, so like I can jump to the optimal maximum.
You can change alpha during training, and that's something that advanced, more modern algorithms do. They adjust the learning rate. Traditionally, you started with an alpha, and that was it. Now you can do that, but you don't need to do so. What you need to do? You don't need to always pick the best action, because this is the best option as far as you know, but you only explored this solution escape, which may mean I only explored that part of the environment, that combination of action, not all the possible combinations. So usually, the best answer to how do I escape a local optima in reinforcement learning is do a random action. Don't always stick with the optimal action, do a random action. Only by not sticking with the optimal action, you can climb up the saddle and find the optimal. And this is a very critical thing to do, because doing random is not good for an engineer, no? We don't want to do random. But if you think about the maze, I don't know, here is the starting position, here is the goal position. Let me see what I can do. I can do something like this. Okay. So let's say this is a wall. Okay. If I got here, starting from here, I did something, I got here. If my reward is the distance to the goal, if I always chose the optimal action, I will never be able to get to the exit. Because I need to accept actions that are not the best action up to now. I need to go farther away from the goal to actually turn around the corner and find the right path. That's something difficult to do, because either you do it by chance, as I said, randomly. Let's try to keep the possibility open to do random actions. Nowadays we have more advanced techniques that usually in some way or another use the concept of entropy. So by doing this action, did I get any entropy in decrease with respect to the previous value? No, because I did a known action and I ended up in a known state. Is there any action that leads me to a state with higher entropy that I still don't know about? Yes, okay, do that. So it is not really random, it's more, you have you have some way to measure when to do a random action and when. So again, the point that I would like you to take home is fast learning doesn't mean fast learning to the correct policy, to the optimal policy. It just means fast learning. And so the oscillation that the stability that I have here, you can depict it in this way, so doing jumps or more carefully exploring. And you can also depict in another way. That was the solution landscape, no? Let's assume instead this is the landscape of the reward that I sampled. Stability or instability usually can be seen from the plot of the reward. Here are all the time steps that my agent interacts with the environment, and here is the reward. Instability means after, I don't know, 10,000 steps, my graph plotting the reward in each step is like this. It is very difficult to understand whether the agent is learning something or not. you are mostly randomly sampling rewards because probably you change too much your values and you can't stick with the right path. If you have instead lower alpha, usually your landscape could be something smoother. So you start with very low rewards, a bit of oscillations, and sooner or later you will find a path, hopefully, that leads you to the optimal policy or close enough. Okay. So, okay, we have this hyperparameter. Why? It wasn't there before in the closed form formulas, no? When we knew T and R. It wasn't there because we didn't need it. We didn't need to rely on the samples more or less. We had the perfect calculations, the perfect number. We didn't need to use a value to establish how much do I trust my estimate. There was no estimate, only a calculation, an exact calculation. So now instead, do you need the learning rate? Because whatever you put in X, that's not the actual value, state value. That's not the actual state action value. That is an estimate. And so another way to see alpha is how much do I trust my estimate? That's why, for instance, one naive but honestly legitimate and also on average it works very good to change the learning rate dynamically is to set the learning rate low at the beginning and high at the end. The more I collect examples, the more I trust my estimates. And this is the disclaimer. You converge to a policy. We don't know if it's the optimal policy. Okay, so we didn't do the hard part of the job, so deciding what to put in place of X. It is a hard job. As I said, it means inventing a new reinforcement learning algorithm. We don't do it here now. So we look at two examples, SARSA and Q-learning. Q-learning is probably the most famous algorithm in single agent reinforcement learning. But let's look at SARSA first because SARSA is a bit easier. The main idea to try to estimate, okay, the quantity that I want to estimate is use the experience tuple. So to try to give an evaluation of how good it is to be in a given state and do a given action, I use past information that I sampled from that state and that action. So as we said, until the agent doesn't get to a specific state and doesn't choose a specific action, we have no information. So before starting to do this kind of evaluation, so to apply the formula, we needed to start sampling what here we call experience tuple, trajectory, rollout. It depends. Unfortunately, the field is full of synonyms. So experience tuple, trajectory, rollout, more or less they means the same. It means what I said before. The experience of an agent is basically a quadruple. Old state, action, new state, reward. Only with these four ingredients, I can try to say, as far as I know, let's say from my only sample, I did one action. As far as I know from my only sample, doing action A in state S was good. I got a reward of plus 0.5. So your X in SARSA is the current reward plus the discounted Q value of the next action. So basically here, contrary to dynamic programming, in which you, before doing any action, can foresee all the consequences of your action, right? So in a sense, in dynamic programming, you go from the present to the future. You can predict the future with 100% accuracy. Now we do the opposite. We don't do anything until we sample a reward. When we sample the reward, we go back. We go back and we start, in a sense, back propagating, that will be a term in deep learning. We start back propagating the reward that we sample on the path that we follow to get to that reward. This is, again, it is easier with an example, and we can pick the greedy one example. If this is the goal, let's assume there is only the goal. It doesn't matter if there is a fall of a cliff kind of situation. It doesn't really matter. This is the starting position. I cannot do anything until I get to the goal. This is the only time where there is a value. This is the only tile with a value, plus 1. So, all these, let's say, experience tuples have current state, current action, next state, and 0 that will be the reward. So, there is nothing, no value to propagate. No value to sum, no value to multiply, nothing. I got nothing if I have a sparse reward scheme. Okay? The first time step in which I can start to estimate the value function is as soon as I get some value. In this case, only the first time I get to the goal. Let's assume that I get to the goal doing this. Trial and error, random policy, it could be. I can go backward, okay, whatever. So even maybe I went backward. So here I went backward, here I went backward, here I went backward. So let's assume that I get to the goal at a time step, I don't know, 23. 23 actions before getting to the goal. Only now I can start saying, as far as I know, given that I got a signal of whether I was doing bad or good, I can start to give values to all the states and actions that I visited. I don't know, 0.3, 0.012, 0.5. Only when I get to a value, I can start saying, in a recursive way, okay, I got to the goal finally, I follow this path must be good, as far as I know. I have no idea in this moment that there is a much better path. I have no idea. So, as far as I know, at the time step 23, if I am in this position, my best action is go up. If I am in this position, my best action is go right. That's all I know. After many times, okay, 23,000. I took different actions in the same states, ending in a different state, so I start to sample, ideally, every possible combination. So, what does it mean here, every possible combination? I visited every tile, and in every tile, I chose every action, at least once. that will be exhaustive exploration. I explored the whole state space, right? Only then I can be more confident that if at the time step 23k, my best path is this one, if I don't have a ground truth, so if I don't know what the optimal policy is, I cannot say yet. But for sure, I can say that this estimation is much more confident than this estimation. Because I have more samples, more experience. Okay? So, here the idea in SARSA is actually to use the tuple, the states that you visit, and be mindful of this weird thing. You use the next state to estimate the current one. It's a bit weird, but it's exactly what we said. We needed to first get to the goal to be able to estimate the value of the actions did up to that point. We can no longer foresee the future. In dynamic programming, it was the opposite. You estimated the value functions of the next states based on your current knowledge of the state transition. Now it's the other way around. I don't know if you're familiar, so if you don't know what I'm talking about, just forget it. This is the same as doing Monte Carlo sampling. If you have an optimization problem, you cannot explore the state space. You can do Monte Carlo sampling. That's everything you can do. So again, if you don't know what I'm talking about, fine. But maybe if you know what Monte Carlo sampling is, this is easier to understand this way. In every state, you have 4 possible options: left, right, up, down. Right? So this is the first tile. This is tile number. If I go left, I go in first. I stay in first tile. If I go right, I go in tile 3. If I go up, I go in tile 2. If I go down, I stay in tile 1. Right? Makes sense? How can you call it? I don't know. It's it's a state visiting function. I don't know, but if you ever see something similar. Again, if I go left, the same. You are stuck in 1, right? So, did I convince you that this upside down tree is endless? Potentially it's endless. So you can't, as a Stephen, you can drop out. I was already in 1, I did L, don't do this anymore. So you can prune the tree if you did the same exact thing. And by pruning the tree, you can find the actual tree. It will be huge, even if in a very toy problem, it will be huge. Well, there are problems in which this thing is so huge that you have no chance of exploring it all. Is an NPR problem, is intractable, you cannot explore everything. You do Monte Carlo sampling. Let's try, let's pick R, let's pick this, let's pick that, let's pick that. In optimization, to do so, you use an heuristic. Some reasonable exploration function. In reinforcement learning, you use randomness and your policy that you improve with every experience that you gather. Okay? So that's the thing. That's how this temporal difference learning works. So this is the example of SARSA. You just put this new x in your equation. This is again just terminology, so if you read a paper you know what it's talking about. SARSA is called to be bootstrapped. Is getting up from your own boots, okay? So to estimate the value of the current state or the current state action, you use the next one. Obviously, you can do this only retrospectively. Okay, we don't know the state transition function. Here is just to show that the function is very similar to the Bellman equation. Simply, we replaced knowledge of the transition function and of the reward function with a different target, x. And if you see this similarity, in the Bellman equation, you add knowledge of the transition function and of the reward function. Okay, I rewrote the old equation in this new way just to make more evident the similarity. This quantity here in parentheses is called the TD error, temporal difference error, Y error. Since you have a minus, this is the error in the estimation that you made previously. This was the old Q value, this is the new one. Okay, so every time you correct your estimate, with every new experience, with every new sample in your Monte Carlo sampling, in your interaction with the environment, you correct your estimate. That's why you need alpha now, because you are never sure that your estimate is correct. You don't know the ground truths. So you need a parameter that helps you decide how much to trust your estimates. So having a lower alpha means I don't really trust my samples. Having low alpha means either alpha with one sample, I am very confident that that sample is very informative and I learn a lot. With alpha low, I can get the same effect with, I don't know, 100 samples. I trust each of them much less. That's another way to see the alpha. How many samples do you want? Does it make sense? Again, this is just a way to put in pseudocode, but again, not every one of you may be proficient in coding, so it may not make sense. But let's start to have at least a glimpse of how to implement the SARS algorithm. Initialize your Q values at the very beginning. Just put everything at 0. Could be nice. For every episode means every whatever number of steps until I reach a terminal state. So if you do Monte Carlo sampling, you need to reach the bottom somehow. You get the state. You chose a random action, or you chose the best action. And this is the exploration we were mentioning, to always leave the door open to escape a local optimum. And for many times, you apply the action, observe the reward, the next state, and you repeat. Everything. Every time you repeat. So many episodes means you need to get to the goal many times. Many steps means give me time to achieve the goal. Okay, I don't know how many times steps do you need. Here we got to the goal in 23 steps. We start doing this. It may be that after 133 steps I still didn't achieve the goal. So usually you put an upper bound here. So you say something like, okay, whatever. After 100 steps, consider termination. So you failed, and start with a new one, with a new episode. Okay. Now let's do another 10 minutes, because this is already the core of a learning algorithm. Okay. So the most important takeaway now is we don't know the state transition and the reward function anymore. So we cannot foresee the future anymore. We actually need to experience the future. So we need to let our agent, in our example here, we need to let the blue dot, the agent, move in the environment. Only when the blue dot gets here or here, I can start reasoning about giving a value to all the states and actions I did up to that point. That's the difference. So in reinforcement learning, you reason on the past, on your experiences. In dynamic programming, or optimization, Monte Carlo, whatever, you reason on the future. You know everything, you can just predict and imagine the future. Okay?